All right, 2 o'clock. Thanks for coming, y'all. Let's go ahead and get underway. Appreciate everybody coming. This is Ramon's thesis defense. He's going to talk to us about machine vision and assessing percent wood failure. Important for any adhesives development in the wood arena. So thanks for coming. Dr. Stokes, Dr. Green, good to see you. Ramon, please.
Okay. Hi everyone. Thank you for attending and welcome to the thesis defense on assessing wood failure in plywood by deep learning semantic segmentation. I'm Ramon Oliveira, as Dr. Rubin said, and I would like to thank you, Dr. Rubin, my advisor, and the committee members, Dr. Bev Stokes and Dr. Greg Berger. We start this presentation, have a field overview, and then start with the introduction and going through methods, materials, results, and conclusions. Let's see the introduction. In the assessment of wood failure, this is a quality control test in plywood production. And in general, the plywood specimens are tested in terms of mechanical shear strength test, wood failure percentage, and also water resistance. We're going to focus on wood failure percentage, and this evaluation is conducted after mechanical shear strength test, after the failure of the specimens and mechanical shear strength test. And why we are evaluating that? Because with the wood failure, we are basically roughly evaluating the strength of the adhesive and the wood. What we would like to know is the quality of the bonding. And for example, if we have 80% of wood failure in that area where occurred the shear failure, that means that our adhesive was stronger than the veneer, than the fiber. And so we would like to see that in a good plywood. That in this evaluation of wood failure percentage is stated in ASTM D5266, but this standard is described in literature as highly subjective. But why highly subjective? Because the evaluator needs to mentally calculate and estimate that areas, the wood failure percentage in that areas. And in case of the plywood, the areas that we are talking about is 1 inch by 1 inch, so small areas that we need to look into that. And also, the results from different evaluators could be different as well. The evaluators could give different results, giving wood failure percentage on the same specimen. And we have problematic readings in the range of 30 to 85%. That's stated in ASTM standards as well. Knowing that, we're going to talk a little bit about subjectivity in this evaluation. I'm bringing to you 2 types of plywoods. One with phenol formaldehyde adhesive and another one with a bio-based adhesive. In the area, in the red squares here, you have the indication of 1 inch by 1 inch area that the evaluator would be evaluating the wood failure percentage. And you can also notice that the color of the adhesive could affect a lot the evaluation. And I would say here for this first one, we could have 80% of wood failure. Also, yeah, here we don't have exactly a good image because of the projector, but it's really difficult to distinguish what is the failure in the wood and in the adhesive here. I would say in the second one, 75%, the third one, 40%, and the fourth one, 60%. And of course, here we have we can decide better what exactly was wood and what is adhesive. So this is one factor of subjectivity in this evaluation. Also, the source of light that we have when you're evaluating the specimens and biases of each evaluator, and etc. And because of this, we are proposing the machine learning and artificial intelligence, let's say applying the deep learning and semantic segmentation through convolutional neural networks to classify plywood, wood versus adhesive failure proportions from shear failure image. This is our general objective, and as specific objective, we have verified the effects of image size and data set split on the CNN training, and also compare the predictions of the CNN models in one data set, the task data set, with the visual estimates in the same data set following the ASTM protocol. The visual estimates here are estimations made by evaluators, external evaluators. With that, let's go to the methods and materials of this research. Here, for the first step, we have the panel acquisition and production. We are working with 3-ply plywoods. In this research, we're working with 4 types of plywoods. The first one we labeled as CH. It's a commercial with a yellow poplar veneer and a soybean adhesive. The second one is CS, another commercial with southern yellow pine veneer and phenol formaldehyde adhesive. The third one is a CT. It's a custom with a yellow poplar veneer and a cottonseed adhesive. And the fourth one, SB, labeled as SB, is another custom with yellow poplar veneer and soybean adhesive. All the customs we prepare here in the Department of Sustainable Bioproducts, and the commercials we just bought in retail branches were available in the market. But here I'd like to point out that we are evaluating a lot of bio-based adhesive, is that our department is talking about sustainable bioproducts, and we are applying our new technology on that products too. Following on in the specimens preparation and test, we got all the panels. We prepare all the specimens following ASTM D906. We got the specimen prepared. We test all then and measurement in the test machine, also following the ASTM D906. After the rupture, we have 2 parts of the same specimen because the specimen has rupture in the inner layer of the specimen, and we storage all the specimens to have all them separated by the type. So now get the image acquisition. We took pictures of just one of the exposed areas of the sheared areas with a smartphone and using wooden apparatus here to standardize the distance between the lens of the smartphone and the specimen. This distance is 36.5 millimeters, and also to standardize the position of all the specimens through this process of taking pictures, because we were taking pictures of a bunch of images, and this helped us a lot. And after that, in the data engineering, we got all the raw images. We processed that to get this square area of 1 inch by 1 inch from this image, and also we convert all of them to 512 by 512 pixels. Using that, we labeled all the image using the Label Me application in Python. Using that application, we can mark all the areas are referent to wood failure in the image. And here is one of them. And using also Label Me, we got the RGB masks after that label, where in red here is wood failure and black is adhesive failure. And this is a cement segmentation. We are using cement segmentation. For this, we're using the image and also this segment mask for solve this challenge, let's say. And going on in the data sets design, we got all the image and masks to create 3 independent data sets: training, validation, and test. These first 2 we use in the training process, but the validation, we also got the model's performance on that validation data set. And the task one is our task on fly, where we compare the visual estimates and the model's prediction on that data set to know really how our model is performing in a totally different data set. And we're using also two factors that could affect the training process: image size and data set split. We're using 4 types of resolution, say image size, and 3 data set split. Going through 64 by 64 pixels to 512 by 512, and changing the data set split, the proportion of data set in training data set and validation data set through 70% training, 30% validation, 80% training, 20% validation, 9% training, and 10% validation. And with that composition, with these 2 FX and 4 image sizes and 3 data set splits, we got 12 models to training in different configurations, and we trained our model with different models with this configuration. Each of them is a unique model because it was trained in an image size and data set split configuration. Moving on, and it's still in data set design, we have here a breakdown of all data set splits, training, validation, and test with the amount of image correspondent of each panel. But here I'm pointing out that, for example, in the 730 split, we have 148 image in training and 65 in validation. And the proportion of image in validation, in training, will increase in 9% training, here 193, and in validation we reduce 22 image. And in the test data set, we got 10 image for each type of data set, or each type of plywood, and 40 image in total. For the model training, test, and performance, we choose the segment architecture. This architecture was proposed by Badri and Narayanan et al. In 2017, and this is a scheme of that architecture that we were replicating that architecture in our algorithm, and that was implemented using Python and Keras and TensorFlow library. So that's a Python language with using Keras and TensorFlow libraries. We trained our models with the add-on optimizer and dice coefficient metric and dice loss function. We test the performance of our models with accuracy and F1 score. Accuracy is a well-known metric for measurements in machine learning, but we are focused on here the F1 score because it's give to us a better balanced result, because it's will penalize the model when is predicting the pixels or classifying the pixels when it's not doing correctly, when it's doing bad in false positives and false negatives. And the visual estimates, where we made a round-robin data collection. We collect wood failure estimates from 5 evaluators on past data set. They follow the ASTM D5266 procedures, and they give results within increments of 5% as ASTM say. And for the comparison, compared the visual estimates and models performance, we made the direct comparison with standard deviation, error using the visual estimate, the average of that 5 readings of the evaluators, and the model prediction, mean absolute error, and linear regression. After that, we have the results. Here, our first result was that our models trained on the image size 54 by 54 and 128 by 128 were not performing well, and this is because of the loss information through the compression of image. We were compressing the image and also the segmentation mask, and so you can notice here in the 512 by 512 pixels that we have a ground truth wood failure of 45.7%, And when we compress that image and mask, that becomes 63%. And when we compress even more, it's going to 79.7. And so that's not exactly giving to us the real wood failure percentage as here. And we are not reporting this for this point, just the other two resolutions, 256 by 256 and 512 by 512 pixels. And here we have the metrics for the models trained on 256 by 256 and 512 by 512. I'm pointing out here the models trained on dataset split 9 and 10 for both image resolutions, and that have here in the F1 score of both of them in 84% and 85%. And that means not exactly true accuracy, and this is because of what I told you before. This F1 score is giving to us a result with giving a better balance, penalizing the models that are not classifying well the pixels. In here we have the learning curves, where in orange here are the dice coefficient in training, and red is the validation dice coefficient. And with that, we know that our model did not overfitting, did not memorize all the data in the training, because we don't have a U shape here. And also both models got almost 90% of dice coefficient with less than 20 epochs, without seeded models 20 times, just less than 20 times reading that data sets. The model was able to get almost 90% of the dice coefficient here. But we have some room for improvement here, because the model did not make close to 100% in validation. And so that means that we have independent data sets, because the model has some features in validation that was not seen in training. But we could increase our training data set even more to have here a really better result. And here is an example of validation data set, where in this first column here we have the model training on 512 by 512 image and 9 and 10 data set split, and the second one 256, the model training on 256 by 256 image, and also with 9/10 data set split. Here we can also see how the ground truth was affected a little bit, but the model also was able to capture, identify that parts of wood failure in both of the resolutions and in all of the plywood types. And that's a good result for us to identify that even both of models, the CNN is getting that pattern of wood failure in both in the 4 plywoods. But here, also pointing out that the last resolution is making a rough measurements, like agglutinating all what is exactly wood failure. That should be also compared to a human behavior when you're looking into area and just putting, oh, this could be some kind of this area as wood failure. And here, going on, we have the direct comparison with standard deviation. In x-axis here, we have the specimens in ascending order of wood failure, and the percentage of wood failure in Y. In black, we have the average of visual estimates with the error bars representing the standard deviation for each of this measurement. Each of this measurement is an average of 5 readings. And in pink, we have the model training 512 by 512 resolution, and gray, the 256 by 256. You can see that the model training on 512 was following better the average visual estimates, and the 256 was within the up range of the standard deviation of that visual estimates. This week we have a little bit of over predicting compared to average visual estimates, but it's still following that increasing of wood failure in the pattern. Here we have the black spots of the error, the results of visual estimate minus the model's prediction for all the models you get, for all the types you get, all plywood stacked together, where you can see the same characteristics that we saw before, but here, as we have the visual estimates here, seems that visual estimates is sub-predicting or sub-estimating the wood failure compared to the model training on 256 by 256. And the model training on 512 by 512 in pink here, you have 50% of our error within 4 and -7, what is really good for us, and the entire error in the range of 20 to -20 in exactly units of percentage. For the mean absolute error, where you can notice that the model with 512 by 512, 512 by 512 was doing really great for in all of the plywood types and in the overall as well, with a mean absolute error of 6 plus a -5. But also I'd like to point out here for 256 by 256 that in the CS, where we have the southern yellow pine veneer and phenol formaldehyde adhesive, this model was doing better than for the others plywood types. Maybe with that rough wood failure, the model was also able to learn some characteristics of that wood failure and get good results here. Moving on, we have the linear regression, where we have plotting here the results of the model's prediction, and here the visual estimates and why. And we got in pink again the model training on 512 by 512, where the R squared is equal to 87%. That means that the variance in the model's prediction is can explain 85% of variance in average of visual estimates. But also I'd like to point it out that for 256 by 250, the model training 256 by 256 was getting R squared of 80%. That is not too bad. And so with that type of compression and all things affecting that learning, the model was able to get some characteristics of wood failure. And in conclusions, it is demonstrated that feasibility of segnet, but also would like to expand this for convolutional neural networks. We showed this one, but we have even better networks now running, and the image size did not affect did affect the model training, and the data set split did not affect the model training on 512 by 512 pixels, and the model training 512 by 512 image with the data set split 90-10 performance had the best performance and well correlated with average visual estimates. Those are my reference. Here I would like to thank you, Mississippi State University and the Department of Sustainable Bioproducts for opening this opportunity to pursue my master's degree, and also USDA and Forest Service to funding this research.